My name is Tobias Eifler, and I was really happy when Kevin asked me if we can do this presentation, and thanks for the invite, of course, Oscar, on the topic of robust design. I'm associate professor and we're leading a small research group here at DTU. And the topic for today is, or we chose the headline, 6 Fundamental Robust Design Ideas for Direct Use. So what we are also particularly looking forward to is the question or the discussion on how to actually implement this idea, which is admittedly quite old, better in a practical environment. And this direct use already illustrates this basic idea, this basic intention today. And that is also the bridge towards our motivation. And I guess all of you have heard about robust design know Takushi and this initial idea of robustness, which was promoted in the 70s in the US or earlier in Japan even, to actually design quality into products. And what we want to today discuss is a bit this idea, where are the from a design perspective, where is the initial idea of robust design methodology potentially incomplete, and what are different research directions which are valuable? And one of the things which is of course clear is while Takushi promotes this use of cross-area experiments, that this is usually relatively late in the process. And I guess that we will find throughout the entire presentation today this idea either to move it earlier on, to front load robustness decisions into earlier design stages, as well as how to make it something that is not an expert task anymore, which is unfortunately out of experience in industry often stays due to the use of statistics, and how to actually bring it closer to the needs of designers in practice. With that, a short overview of the presentation, and I'm not going too much into detail as Kevin will probably elaborate on a later slide a bit. So what the general structure will be, we will start with the traditional things, with the discussion how to implement that potentially easier in actual design practice, and then move slowly up in the design process, how to implement these ideas earlier on in these cases. And therewith, I would hand over to my co-speaker, Kevin. You just let me know when to switch.
Sure. So a little motivation from where I'm coming from. You know, we need more of this in practice. We need to teach more of this. We need to get people skilled at this. We need this to be deployed and adopted by companies. And the reason for that is, you know, things are getting more and more integrated and complicated and harder to design. We see this in the complexity growth of systems. Here I'm picking on the airplanes. I don't care if you talk about Boeing or Airbus, right? The development times have been getting extended beyond what was planned and continues to be this way. And so you can ask, well, why is that? And you know, if you look over on these latter ones here, you see this growth in activities that's happening when they think the design is done, and we just gotta, you know, build it and integrate it, get it working, you know, getting harder to do. So go ahead. And so here's a real example from the 787 that I did work on, a cooling unit. The first prototypes, they worked great. All right, they were just fine. They did what they were supposed to do. And then it get into, you know, initial productions, and the units that are being built, they get to their end of line test, and they're not exhibiting the performance that that they thought they'd have. All right, they're overheating and not delivering. All right, and why is that? And so now you get into this whole root cause analysis, sort of difficulty to figure out why. And at the end of the day, is because they tried to make it too lightweight. And they took design margin out, and they brought it closer to its limit than they realized. All right, and the tolerances were never really analyzed in terms of performance. All right, and a realistic set of tolerances. There were some geometric perpendicularity misalignments that was causing gas. Anyway. The story is the tolerances had in their nature regions where defects would arise. All right, and you know, you can sort of see it on the right-hand figure there of what happened, where there are some combinations, you know, of variations that cause performance to not be what you want. And it's really hard to detect, all right? Can be, without tools. So go ahead. You know, you think that you put in a safety margin and, you know, how do you decide? Well, you know, as long as the applied stress is less than the strength, it'll work, all right? But just because what you design in and test at your nominal first prototype doesn't mean the full line of production is going to be that way, all right? There's going to be variability that happens that will generate a probability of failure, and that's what you need to control. But determining this in the design phase, right, can be hard, right? So go ahead. So we're going to talk about 6 different methods that I've used in practice, that Tobias has used, people use, that we can use and should be cognizant of when developing mechanical systems and to increase robustness. And we're going to start with good old Taguchi robust design, right? Number 1, quality engineering. But that, you know, you really do have a concept, you have an embodiment, and now you're trying to improve it sort of phase is where that's, you know, you would argue perhaps appropriate. But there are other methods that are appropriate earlier on, all right? So we're going to walk through them from late phase all the way back up to, you know, when all you have is a concept, all right? What can you do, right? And we'll talk about what if you're thinking about just the functionality of the system. All right, is it a good way of solving the problem? If you have a design implementation, all right, where you're thinking of what the parts are, you ought to do a design for assembly analysis. Trade-off eliminations. The reason that you have that the margin got small is because one thing's driving it to be large and another thing's driving it to be small, and you compromise. All right, and your margin, you know, suffers. And a lot of these can be better improved mechanically if we think about how we're kinematically constraining and putting the assembly together. So we'll talk about all these. We're going to fly over them in some sense and show you what they are. But these are the things that we spend time on in the robust design SIG, among others, and you know, want to disseminate and improve. All right, go ahead. So a less sensitive design. There's the famous figure. You know, we have a particular setting of the design on the input x-axis. And if we're on the left side, if there's variability, then we're going to get a lot of variability of output. And the idea is, can we find a collection of input combinations, you know, make something a little thicker, make something a little shorter, so that we can get to a place where there'll be less variability. All right, go ahead. So this is Taguchi's robust design method, right? We set up a design of experiment on design variables, so big design changes sort of shown in the box. And at each of those, we do another set of designed experiments across tolerances, let's say, across variations, across noise variables. And so at, you know, a design of experiments of design variables, a design of experiments of noise variables, you end up with, you know, potentially with this big array matrix of experiments to be done. And apparently people did this a long time ago. All right, here's stories of, you know, the car companies in Japan doing these design experiments with, you know, hundreds of experimental prototypes, and wow, right? So it's a lot of work, can be, all right, and it's complicated. And, you know, to get this set up, you know, and to be able to analyze it, you know, is hard. So it's been slow to adopt. All right, you know, the studies are showing this. It's something we keep learning and relearning and relearning. If we do this experimentally, it's really tedious. All right, but there are books that have been around on this since, you know, the 80s, if not before. Here's a collection of them, and they're good, all right? So go ahead. What I want to point out is that if you're at the phase of studying your design with simulation tools, which are more common and accessible today, all right, it's actually easy to do robust design analysis, all right, because there are modern open source code libraries that you can use to set this up, to do these calculations really quite fast and simple. Right, in terms of uncertainty quantification. So how much variation is there? Let's generate the histogram. Why? What variables are most important? A sensitivity analysis, right? Snowball indices, the Pareto chart. And if you construct these, you can fit surrogate models to the results and set it up so that you can do optimization studies, all right, of the results. So go to the next slide. All right. All you need to be able to do is set up your analysis tool, right? Whether we're talking about ANSYS or whatever, set it up so you can script it. If I have an input file of variable names and variable values, and I have a batch file that reads that input, runs the simulation, and extracts whatever metric of interest that you want to create your histogram of, saves it in an output file. All right, if you can build one of those, all right, then there are tools that will replicate this 1,000 times, do the Monte Carlo simulation, show you the UQ, show you everything you need to know. This is all you need to be able to do. All right, there's a Python, code lab. Code in a Jupyter notebook. It's really fast and simple. All right, go to the next slide. It'll generate the histogram. Go to the next slide. It'll fit a reduced order model to the result and compute the breakout of variance. And then you can use that to solve an optimization problem. If you have your original design, you can minimize, keep this target on target and minimize the variance. Just go straight down. Maybe what you want to do is increase the power with that amount of variance, right? But you can compute the whole entire Pareto frontier of power or nominal and standard deviation, right? And pick where you want to be. All right. So this all exists, all right? And, talk to us afterward if you're interested. But it's all available, and it makes this simple. I've handed this Jupyter notebook off to friends in industry, and they're up and running in a matter of hours, not weeks, if they can build their simulation tool like it's structured. All right, so that's something that I think people should be aware of. Go on.
I think here I take over again. So going from these basic ideas and the simplification or the simpler version of implementing them that we have at hand today, I move one step back in the process, and I focus more on the question of what is actually the structural aspect of a design. So this topic, constraint tolerancing, is also nothing new. I think it's existing since with books since at least 80s or beginning of the 90s. And the reasoning is simple. Usually when we talk about geometric variation as one of the main influences in the mechanical assembly, we start thinking, or also we start teaching students to think about tolerances. So what are the necessary tolerances? And out of our perspective, that is of course basically far too late. You should think about the design change, and that is exactly the idea we would like to promote today as well. So here it's an example from good colleagues at Chalmers University who focus a lot on the actual definition of locating schemes. So every time that I would like to put together two different parts, we will need to define actual contacts between these parts. And that is not just an exercise to make the system work. You can also make your system more robust, less sensitive, how this geometric variation is actually propagated. So when thinking about a relatively simple locating scheme, this 3-2-1, the basic idea is we need to log all the positions, or we need to define these positions. And with this example on the right-hand side, I guess it's pretty clear that this locating scheme is a little exaggerated bad and leads to quite a lot of variation. So simple rules exist that allow us to really rethink these locating schemes and really distribute in a better way the contact points on our parts to reduce the actual variation. And in a nutshell, summarized here, that would basically mean that decreasing coupling in these locating schemes reduces the actual variation that propagates through our assembly. And even more from these calculation principles, which is already existing in software tools, we can also derive a couple of design heuristics, which are basically, out of our perspective, should drive all design decisions. So things like that we can spread locators to increase the robustness, reduce sensitivity, shift locator order to decouple, so not just randomly define how parts fit together, but really rethink the way that we are creating the assembly. Avoid secondary effects. So also when I position locators according, for example, to the center of gravity, I will avoid coupling between different degrees of freedom, which are also making the system or the assembly more robust in this case. And one of the important things is also that, of course, the clarity, how clear we can design our system, will increase not only the robustness, but also the analyzability and all the efforts that we make to actually later on, usually, to control the variation that we see. So we run a lot of tests, we run a lot of simulation, and we just not find the issue, which we should have probably avoided earlier on in the process. And particularly for this analyzability, there's one step earlier even. Here we think about an exact constraint design. So we have clear contact points. We have not too many contact points. We have exactly the kinematically needed contact points. And what we did in our research a bit here, it's another example that I adopted, is thinking about exact constraints. And so this is an example I adopted from a book, I think from Coda Company, at some point in the 90s. With a paper feeder, where exactly this notion that Kevin already described in the design, so that we are basically building something and in the end we try to fix it, is actually really nicely shown. So the story goes a bit like this, that first of all, we design a system of a paper feeder, and without considering that the parts are actually positioned already, we just put another additional part, this curved piece in the middle between the two parts, and hope that it works. We're not really evaluating the system. We're not really analyzing the system. And in the beginning, the paper jams in the system, in the paper track, due to distortion that we have, because we have over-constrained the system, and we're adding basically to our design. We're adding reinforcement bars. Suddenly the curved piece distorts. We're adding a reinforcement bar to the curved piece, which is the second picture. Then suddenly the screw tabs break. So we're basically creating, instead of really thinking about our system, we're creating new problems, and we're basically making it even worse. While in the end, a solution could look like the following: just a relatively simple slot mounting of this curved piece, which allows us to adjust to variation in our process. This idea is relatively nicely illustrated here. Is of course basically, can we avoid these constraints in the system early on in the process? And a bit of research that was done in our research group some years back then took this idea even further towards what are principles, what are kind of catalogs that allow us to pinpoint these issues early on the process. And one of the examples that I would like to use today is basically a list with principles, ambiguity principles, to just go early on through our embodiment and say, okay, what are critical interfaces? What are interfaces that might need extra effort or extra attention? And simple examples could be large contact surfaces. So how, do we have a chance to actually reduce contact surface to make a clearer design, a better understandable design, which we call then predictability? And another example, also relating it to this idea of coupled locating schemes, are angled interfaces. So when I have in some way positioning through angled interfaces, of course, we're coupling two different degrees of freedom, two translations in these cases. And when we can avoid these things, of course, we cannot always, but when we can avoid these things, we usually have a simpler system that is not as susceptible to variation. And in the end, that is not only making our system more robust, but also avoiding exactly what we said before, this effort that we have in the design process. We have simpler drawings. We can better explain where the system is actually acting. We have a clearer communication of the design intent, and we can also it feeds also directly in what Kevin has presented before. So we have an easier time to actually build our models and then go into complete details of simulation in these cases. And that, of course, and this is just an example from this GM ignition switch, which you had a look at. And I guess you know this case where GM had to recall quite a number of some cars. And I think these simple principles were not necessarily considered in these cases. And that relates then also to directions of forces, the lengths of tolerance chains, the whole consideration of how are we actually putting together our assembly, how are we defining the different interfaces. And that in itself is, of course, quite of some value already. And where we move to in our research then, that is, of course, also, as always in research, or as often in research, we picked some ideas which were also existing before, which we looked into trade-offs. So while this idea of kinematics is, of course, quite valuable also as a principle for designing, we realized in the system that we're usually working with, which is a highly integrated medical device, we realized quickly that the practitioners told us, okay, we cannot just separate everything or design interface because we have so little space actually available for this whole thing. And that made us realize this move towards higher and higher product integration, which is just continuing with more and more connected devices, with more and more domains that we're actually designing with. In these cases, that leads to trade-offs in these cases. And trade-off, we understand as a design variable, which should be which should be minimal and maximal at the same time. So in this case here, we have one design variable and two functions, simplified visualization. And of course, we have in the end a relatively small window of opportunity, so what we call the sweet spot, and we need to make these compromises. And usually, of course, in the system, we have not one trade-off, we have a lot of trade-offs, and the latest, when we then hand over to a test or to high volume production, suddenly the variation increases and everything falls apart. So this one idea of trade-offs, avoiding trade-offs, can help our robustness of the system, and of course also with a quite high impact on the iterations that we see today, as Kevin illustrated in the beginning. So these compromises, out of our perspective, are exactly these questions where we iterate and the design process gets longer. We're going jumping from one solution to the next and trying to find in some way the only feasible compromise between all our function requirements. And then perhaps a little more from the academic side, also one of the things which is interesting. So particularly when we are looking into mechanical embodiments, these trade-offs can not only result from the functional trade-off, so when we really have functional variables, but trade-offs can also result from the actual structural build of our system. So from all the topological loops, from constraints and material properties, and so on and so on. So we are basically combining with this topic the two things that we had before, and we can use it relatively early on in the process. And that is exactly what I have here on the next slide. So just two ideas how to actually use it, and this particularly really easily implementable. So what we looked into, and what you see here on the slide is exactly our case product, an insulin injection device from the medical device company here close to Copenhagen, Novo Nordisk. And what we went with to actually look into these trade-offs was a purely manual evaluation by the design engineers. So we looked into, on a simple scaling, how are different parts or different design variables actually contradicting? So manually evaluating them across a number of function requirements and then summing up these contradictions either in the row to identify critical parts, critical variables, or also in the columns to actually say which are the functions that we actually need to spend more effort with. And that is not completely representative, but in the first evaluation, we looked also a bit into what is the number of demanding tolerances. And actually, there's a quite nice correlation, particularly on the tolerances, between narrow tolerance windows that are specified later on the process, which basically cost money in the end, and this contradiction number that we have manually evaluated, and even to the design iterations that we checked with design change notes, there seems to be a link to these parts. And then to now we moved all the time so upwards in the development process earlier and earlier. Now go back to the more quantitative analysis, of course, with a bit of adoption of then the optimization topic again. Trade-offs, Pareto sets are also a way to actually evaluate these trade-offs when we're really quantitatively analyzing those. We were working on possibilities to actually do that, and then based on these trade-offs, based on the right model, identify exactly the limiting constraints in our system. So can we basically rigorously define design change? So what are factors that we need to actually touch to improve our design? And what you see in this graph is basically just the number of violated constraints. So we have two variables, and the further we go back to the origin there, the more constraints are violated. And of course, the first constraint already counts. So what is the constraint that limits our design most? Where do we need to touch the design to redesign from a mechanical perspective? And that leads then again back to what are we designing? And there we jump to another set of methods, which Kevin will present.
Thanks, Tobias. So, the contradiction index that he showed, and find the parts that have a bad contradiction index, all right? That's where the bad sensitivities are, right? And see if you can design them out. Think about them, right? So I guess I wanted to say, another factor on robust design is to try to make it more simple, all right? A simpler design is a better design. And we've known this a long time. So here's I have a couple design engineering heroines, right? People that I look up to in the past, right? Henry Maudsley, right? Before Henry Maudsley, there was what really wasn't mass production. After it, there was. After him, there was, because we finally got precision, all right? And he had a saying, put yourself the question, what business has it to be there, all right? Look at your parts. Why is that part there, right? Why is that feature there, right? Get rid of it, all right? And another one, Kelly Johnson, right? Led Lockheed Skunk Works and the U-2 spy plane and SR-71, right? Back when we used slide rules. His statement, right? Keep it simple, stupid, right? Get rid of that stuff. Right? Design's not done when you can't add anything. It's when you can't take it when you can't take anything away. All right. So I'm sorry. Go ahead. So we want to get rid of unnecessary parts. So how do you identify those, right? Well, there is methods out there, design for assembly. And designs that have been scrutinized for simplifying the assembly have less defect problems. They're higher quality, they're more robust, data shows it. So here's really old data, but it's real data from Motorola on different devices and what their Bothroyd-Dewhurst, right, assembly efficiency was, how many unnecessary separate parts there are, let's say, and defect rate. And if you can do better on manual design for assembly, you'll have a higher quality system. All right, so simplification. All right, go ahead. So, okay, I want to simplify my design. How? All right, what's a candidate to look at? Where is it? Where do I have some sensitivity here, some weakness in my whole machine, my whole design? Well, they studied this and came up with sort of 6 thoughts of when 2 neighboring parts need to be separate, or can you combine them into one part? Well, they have to be separate if they have to be at different temperatures, if they have to be at different, voltages or different electrical states, right? If they have to move relative to one another, if they have to be a different material for some reason, or if you make them one part, then you can't assemble others, right? You can't make the lid of a box part of the box because then you can't put anything in it. Similarly, you can't get it open to service it, right? So those are the reasons why you need to have two parts separate. If all of these come back no, you should combine those parts into one part, right? Get rid of it, right? Now maybe you can, maybe you can't, but at least you studied it, all right? And look for where the assembly sensitivity is, right? Where is it hard to do? Go ahead, all right? I mean, stupid little thing. How many parts does it really need to be? Go ahead. All right. I mean, we can simplify these to less parts. They're more robust, right? There are less things to go wrong on them, let's say. Now, the last one on the bottom there, of course, doesn't have full constraints. It puts a load, but you get the idea. All right, go ahead. All right, design for assembly. Get rid of parts that aren't necessary. Now let's step even earlier and think about functionality. All right. The way you've decided to put this together to do what it does, where's the weakness in how it's operating? All right, where are functions in here that are not as good as they should be? All right, so here's a motor. All right, everybody knows what a motor is, right? It converts electrical power to rotary power. All right, how does it do it? Well, it's got a collection of parts that do things. What do they do? All right, so not all the functions in this motor exist, to generate customer happiness of a rotating shaft, right? Some are here because we need to take care of undesired effects, because we're not smart enough to get a good enough machine that can do what we want without generating badness. So what badness are we generating? You ought to ask. Think functionally, right? Next slide. All right, so here's all the things it does, all right, in order to convert electricity to rotation, right? We got to input the electricity. There's a place where the wires connect up, all right? It goes into the stator and all that, right? And generates, converts electricity to motive force. You got bearings that allow the shaft to rotate, all right? We get a counter rotation. We got to clamp it. And we got a shaft to transmit it out, and on the back end we got a fan to cool the motor down. All right, so which of these directly address what the customer wants? Those are necessary. Which of these solves problems generated by our poor solution, all right, to providing the necessary function? All right, these other ones that solve problems generated by our bad idea, these are secondary functions. And they act on a harmful flow that are spawned out of a harmful function. So the secondary function is provide cooling. All right, that's not what the customer wants. They just want convert electricity to rotation, and it's there because the windings heat up. All right, so the harmful flow is that heat generated. So go to the next slide. All right, so what we want to look at is this harmful function: convert electricity to motive force. Think about it that way. Can we convert electricity to motive force, do that function, without generating, all right, the harmful flow? If we can do that, we can get rid of all that garbage on the back end of providing cooling. All right, that's the new breakthrough idea we need to be working on to improve our design, make it more robust. All right, go ahead. All right, and people are working on it. All right, it's called superconducting wire motors. All right, generate no heat. The Navy's working on a ship propelled by this, so they can get to the all-electric boat. And this is on the technology roadmap to get there. All right. Yeah, keep going. Another thing that we can do is to think about this. Is to see if there's a way to simplify not just functions within the concept, but get to an entirely better concept that's more robust. All right, so let's think about our machine, our product as simply, a tool that's doing its overall function on some object. So a microwave oven, what's it do functionally? Well, it cooks food. All right, a network card, what does it do? Well, it connects your machine, your PC to the network. All right, here's a glove dryer, right? You hang your stuff on there, it dries your stuff, right? Go ahead. Are there freely available resources in the surrounding that can do the function, all right, without your tool? So if we want to dry gloves, okay, we can get this glove dryer to do it, but are there some other ways in the environment that we can use to do the function? What else is out there? And so you see these clever ideas like these, attachments. You can reuse existing heat sources to dry out your gloves, right? A little attachment onto your car, all right? Less things to break, all right? More robust, less parts, less things to go wrong, right? Go ahead. The story of the modem, right? So a long time ago, there were these things called modems. Your PC cost $2,000, your modem cost $300, and it was a separate box. All right, you connected it to the telephone, and then you had another cable that connected that to your PC, and that's how it worked. All right, and then with the advance of technology, CPUs got fast enough that all the modem functions could be done on the CPU. Because the CPUs were getting faster and faster and faster, and the modem commands were static. And so we switched from external modems to so-called soft modems, and that happened around the late 90s. All right, got rid of the box. It went from $300 to $50, more robust. Right, and then everybody said, well, geez, why don't I just put this on a chip on the motherboard, and then it's only 50 cents, and who cares? And again, it's this idea of getting it done with less, right? Using freely available resources. Go on. And this you see happening everywhere. All right. Any design through its lifetimes becomes more simple, becomes more reliable, becomes more effective, becomes more ideal, right? Costs less. And at ideal, the design disappears, the modem disappears while the functionality remains. It's all on the motherboard, right? Getting to more and more ideal. You see this all the time. Go ahead. So the ideal final result, all right, is the extreme of this. All the benefits you get, the cost all the way down to zero and harmful effects eliminated. That's robust, right? So the idea here is, can we simplify the concept and get to exactly what we wanted, right? And walk away from what we're doing. So it's really radical thinking in a way, but simplify the concept to the point where it's super simple. Go ahead. All right. So the last thing I want to talk about is this itself problem approach. Okay. So think about a microwave oven. What's it do? Cooks food. What's the most robust, ideal microwave oven? Okay. Go ahead. What we want is the ideal final result. The customer wants to cook food, and I want to do that without any problems at all. No electricity. I don't want to wait. Right? I don't want to have to handle it with gloves. I don't want to get microwave radiated. I don't want to take up countertop space. I just want to open up my food and it's cooked. All right? Go ahead. And they're working on it. Right? Here's a can. You open it up. It's cooked. I don't need no microwave oven. All right? Get the thing you're trying to manipulate here, the food, get it to do it itself. All right? Go ahead. All right, so this is the itself problem concept simplification. Eliminate the concept, all right? Find the way for the object to do it. Can we make food cook? All right, go ahead. All right, what's a light bulb for? Illuminate space, all right? So can we make space illuminate? Well, yeah. I bet everyone's sitting in a room right now with the lights on, right? Why? It's daytime. Right, we ought to be having, modern net zero buildings are all daylit, right? They use, try to use the lighting from the sun and design it so that the light gets all the way into the building. All right, it only works during the day. Well, let's work at ways to get the surface to provide light. I guarantee you, paint companies are working on this right now. All right, find coatings they can put on that will absorb light during the day and shine at night. All right, so we don't need light bulbs. All right, clothes that illuminate for you. Remember when backlit light bulbs, backlit keyboards came out? How nice that was? You didn't have a separate light to try to figure out where to put your fingers. All right, when you're trying to keep it dark to not wake people up. All right, make itself do the task. All right, go ahead. All right, so less sources of variation. Design for assembly. All right, where are the weak too many parts? Functional simplification. Where do you have unnecessary functions that are generated because you didn't think of a good way to do the primary function? All right, and then concept simplifications. All right, find other things in the environment to do functions for you so you can simplify it. All right, all the way to the most radical here, the itself problem. And then, of course, all the way once you have designs, right? Eliminating trade-offs, get your tolerancing constraints right, and and then we can get to good old Taguchi robust design. Go ahead.
Okay, I don't think that there's so much to add. I think what you have realized to Kevin's presentation is a bit this idea also of having a robust design SIG in the design society. So what we are completely convinced of that, of course, there's a value in computer-based robust design methods, and there are also principles and tools available to make that easier implementable. But it is in the end an effort which needs to start in the beginning of the design process. So what we can drive by design change is that we are not only making our designs better, but we are actually really enabling an efficient application of these tools also in later stages. And there it is unfortunately where the whole thing falls together often, so that we are designing without thinking exactly about these tools, without thinking about variation, without thinking about sensitivity, and trying to just solve it in the end by simulation or by testing. And what we're providing with the SIG is exactly this idea. Can we implement a robust design methodology, which is not only in the latest stage of the design process, but where we actually look into concepts, where we look into the functional analysis, where we look into the mechanical configuration. So can we improve there to actually make it better? And before we close, just one thing. In this case, we think we would like to put this robust design topic also on the agenda a little more. And we looked at the one silver lining in this pandemic, and that's of course the opportunity to bring researchers better together, and also researchers. And what we were planning was a SIG online research seminar. And what we would like to propose is basically a regular meeting for people in the design community, in the research community who are interested in this topic. And while we focused a lot on mechanical development today, of course, that goes further, that goes into networks, that goes into complex socio-technical systems. How do we actually consider robustness there? And while we have a plan on our website, so go and check that also out. What we would like to propose is also a short meeting after our discussion today. Here's the meeting link. I will put that in the chat a little later on. So if you're interested in joining a discussion platform, a research online seminar, how we coined it, then just let us know. Either drop us an email or join us directly after the speaker series here today. Having said that, I would say on behalf of both of us, thanks for listening, and of course, looking forward to questions and the discussion.